Hello, this talk is about optimization-based user support for Cinematographic Quadrotor camera target framing. My name is Christoph Gebhardt, and I conducted this work together with my supervisor Otmar Hilliges at ETH Zurich. An important factor that affects the visual quality of scenic aerial video shots is the framing of landmarks. In professional aerial footage, landmarks are framed to be precisely positioned at desirable locations on the screen of the video. This creates spectacular compositional effects such as the simultaneously moving foreground and background you can see here. Quadrotor camera tools have enabled end users to design complex aerial video shots in virtual environments and execute them in the real world. However, as their optimization schemes do not model the landmarks users intend to capture, the end-user created footage often feature target objects that are free to move around the video's image plane, causing visually unappealing aerial videos. Due to the absence of target models, current algorithms simply interpolate the camera angles of given keyframes or the intersection points of the center array of keyframes with the virtual environment. This results in videos that feature the camera target all over the image plane, even moving out of sight, while the intention of the user was to let the water tower transition from one line of verts to the other. To tackle this problem, we propose a new cost term that optimizes the decrease of freedom of the quadrotor camera such that camera targets are continuously placed and framed at the desired image space positions. More specifically, we want to position the target at a desirable location on the image plane of the camera. The target framing term then minimizes the 2-norm error of the relative vector between the position of the quadrotor and the target and the vector that projects the desirable image plane position into 3D. With the objective, the water tower is framed according to the rules of verts and nicely transitions between the two vertical lines between keyframes. However, in the parts of the video where the camera approaches the target closely, the tower is not entirely visible. This is corrected by our second cost term that changes the camera's position and orientation to ensure that the target is located within the extended camera frustum in all frames. The cost term ensures that the cylinder that approximates the target is in its height within the top and bottom plane of the camera frustum. The same is done for the cylinder's diameter and the left and right plane of the camera frustum. The resulting video shows that the tower is nicely framed and entirely visible throughout the shot. We propose a pipeline that automatically identifies camera targets from user-specified keyframes. This is achieved by using a state-of-the-art deep visual saliency model whose output can be refined by the user if necessary. Camera targets are then identified by raycasting and point cloud segmentation, approximated with a bounding cylinder, and used as input to our optimization scheme. To evaluate our method, we presented participants with a side-by-side comparison of two videos which were generated with our method and the previous state-of-the-art. Participants had to rate the difference between the two videos on a Likert scale. Results show that our method enables users to design videos that feature a target framing which better matches with what they intended to create. Videos were partly also perceived to be more aesthetically pleasing. Here we compare results generated with our tool to a trajectory optimized by an existing quadrotor camera optimization scheme flown using an unmodified consumer-grade drone. Thank you for your attention.